All right, we're back. We're on page 3, notes 1, Calc D, which is multivariable calculus. We're reviewing some vector type things and a little bit of like just getting our bearings in 3 dimensions, I guess. So let's see if we can do these problems. So we're going to use a calculator to find the dot product of the vectors from -635 to 8, 4, -7, and from 1436 to 5, -47. Show proper calculator assisted work. All right, so what we want to do is let's name these. Let's say A, B, C, and D. And then what I'm going to do is I'm going to make a vector AB, and I'll just write down what the calculator says that is. I'm going to make a vector CD, and I'll write down what the calculator says that is. And then I'll do AB dot CD, and I will write down what the calculator says it is. So let's switch the calculator. So I'm going to define these things. I'm going to find the dot product. So let's see if we can do it. So I want to switch over to the calculator. All right, so I'm going to store A as in a vector -6, 3, 5. Store B as 8, 4, -7. Store C. So I always store points as vectors so that I can do stuff with them. So it's like you can picture the point as the terminal point of a vector in standard position, which means its initial position is at the origin. And if you do that, a lot of problems are just going to be easier. So I want the vector AB is going to be B minus A, and CD is going to be D minus C, because you're always doing terminal minus initial. And then for dot product, I want menu, option 7, option C, which you can just press up for. And then I want dot product. And then you can type them in or you can use the var key. So AB, comma, CD. All right, so I'm going to handwrite in a bunch of this stuff. So AB is 14, 1, -12. 14, 1, -12. CD is -9, -7, and 1. And then the dot product is -145, which means that the angle between the vectors is obtuse, because when the dot product is negative, the angle is obtuse. All right, let's go back to the notes and see. So if you're not familiar with that, you got to go back to the math analysis notes, because that's where we learned all this stuff. Now we're just in 3 dimensions. We're reviewing it so that we can use it. Use a dot product to determine if the angle between the vectors is acute, obtuse, or if the vectors are orthogonal. All right, so let's do some dot producting. So this is what I hand wrote before, by the way. All right, so V dot W is going to be -15, -2, -4, -21, since V dot W is less than 0, theta is obtuse. So if you remember why, it's because the dot product is related to the cosine of the angle between them. So it's the cosine of theta is U dot V, well, here, cosine theta is, let's say A dot B over the magnitude of A and the magnitude of B. So then so the magnitudes are going to be positive. So the only way that this thing could be negative is if the dot product is negative. If the dot product is negative, you're doing the inverse cosine of a negative, which puts you in quadrant 2, because inverse cosine comes from quadrant 1 or quadrant 2. So knowing the sign of the dot product basically tells you the nature of the angle. Is it acute, obtuse, or are the vectors orthogonal, which is kind of the neatest result that we can get. -14 plus 18 minus 4 is 0. So since U dot V is 0, U and V are orthogonal, which means the angle between them is pi over 2. And that's kind of cool, especially in space. Like in 2 dimensions, like, all right. But in space, that's like crazy that that's even possible. I'm going to keep going and just do the rest of these, I think, in this video, because they're relatively quick, maybe, potentially. Find the exact and approximate in radians angle between the given vectors. All right, so what we're going to need is we're going to use this formula up here, right? So I need the dot product, I need the product of the magnitudes. Am I regretting that I said I was going to do this? Maybe, but whatever. So theta is going to be the inverse cosine. So this is going to be the exact value. So I need the dot product, which is 8 plus 15 plus 4. Product of the magnitudes. All right, so 64, 73, 77, I think. So that was 64 plus 9 is 73, plus 4 is 77. And then 1 plus 25 is 26, plus 4 is 30. That's the exact value. For the approximate value, I mean, I'm just gonna punch it into a calculator. So I don't know if, do we really need to do that? I don't know. Let's try this one. So theta is gonna be the inverse cosine of negative 36 minus 6 plus 35 over. So here's what you do when you don't really want to do the work. So, I mean, this one's not bad. 25, 34, 38. I don't really want to simplify this one, so I'm just going to do 144 plus 9 plus 49. These are the exact values. I'm going to use the calculator to like confirm them and whatever. But that, like by hand, that's as good as you're going to get because those do not appear to be famous angles. So let's go to the calculator and see. All right, so I'm going to define V. So like you always want to just be defining things. It's so much easier. I know it's annoying to do it, but like now all I need to do, I want to do the inverse cosine. So you can use the trig key for that. Inverse cosine of the dot product. So that's menu 7C, and then option 3 of V and W over the norm. So it's menu 77 of V, the norm menu 77 of W. And I'm gonna press enter and just see what I get. I mean, like, whatever. Let's get the, let me just check the dot. Oh, I never actually got the dot product though. So I got 23, 27, yes. And then the norms, I think definitely work. Well, I don't know. Norm of V, norm of W. Okay, so those worked out. Let's get a decimal because we're supposed to. So 0.974. So theta is approximately 0.974. It's almost 1, so it's like almost 1 radian, and 1 radian is like almost 60 degrees, so it's like almost 60 degrees. All right, I'm gonna define U, -3, 2, 5. I'm gonna define V is 12, -3, 7. So now can I go up and just use this? Like not exactly because I need to change some things, but I can just do that, U, V, and then I'll put them in the same order because I like that, but could have just changed the W. So exact value, it does that. It does like co-functions. I don't know why. It doesn't always like to give you the thing you think you're gonna get. 1.651. All right, that's good enough. Okay, so now the next thing says, use your calculator to find all values of k such that these two given vectors are orthogonal, show proper calculator assisted work. So I'm gonna just do it because I'm here. So doc 4, I'm gonna insert a problem. I'll call the vectors u and v. So u is gonna be -2k, 3k, 2 plus k. So this is given. V is gonna be 4, 5k minus 2, 3k minus 2. Interesting. Okay, so we want these vectors to be orthogonal. If vectors are orthogonal, the dot product is 0. So I want to solve for when the dot product, that's menu 7C3 of u and v is equal to 0, and I'll solve for k and see what I get. So I get those two values. So let me just like make a note of those, and then I'm going to go back to the notes and I will write down, I don't like the way that it writes the the result of using the quadratic formula, it always does this weird factoring thing. I think it like, I don't know the reason. Like, does it want to start with a radical maybe? I don't know, because like, why not do 5 minus and then 5 plus? That's what a human would do. But I guess it's not a human, so that I guess is why. All right, let's switch. Go. And let's write down the work. So the work that I would show, I think, is this. I would say negative 2k, 3k, 2 plus k, dot 4, 5k minus 2. So it's when you're using a calculator, I mean, there you go. That's it, right? So we knew that the dot product needs to be 0 because if the dot product is 0, vectors are orthogonal. So I write down the dot product, set it equal to 0, let the calculator do the work, right? That's the whole point. And so we have one last question. It's about the direction cosines. Direction cosines, I don't know. They're a thing. How much do they come up? It's hard to say, really. I mean, like this is, can I think of another time they're going to come up? Not exactly. The direction cosines are related to the unit vector, though. So if I find the magnitude of v, and this is like notes, I think 17 of math analysis is where we first encountered this. So I'm assuming you've recently reviewed those. And so you kind of know where I'm going here. Is that 40? Is that 49? 30, 45, 49. That's weird. So 7. It's like a Pythagorean, I don't know, quadruple or something. Seems like that should be a thing. All right, so if I do v divided by the magnitude of v, that's going to be 3/7, -2/7, and -6/7. Okay, so direction cosines are actually just the components. So it's cosine of alpha. So alpha is the angle between the vector and the positive x-axis. And the cosine of that is 3/7. Beta, so cosine of beta is -2/7. Beta is the angle between the vector and the positive y-axis. And then the cosine of gamma. Gamma is the easiest one to actually see, I think, when you have a picture. Gamma is the angle between the vector and the z-axis. So let me say x-axis and vector, y-axis and vector. I don't think you'll have to do much with these, but you never know. Z-axis and vector. So you typically find the direction cosines. You don't find the angles, you just find the cosines. Now, what is the identity that relates them? Well, if you think of them as the components of the unit vector, then it seems pretty clear that cosine squared, cosine squared, cosine squared equals 1, which it definitely does because it's a unit vector. Like, how could it not? Okay, so if you go back, look at math analysis stuff, if you want more practice problems, this is all review, all just trying to get you back in the mind frame of 3 dimensions, vectors, all that stuff. This is a pretty good page. So I'm going to end this here, and I will be back in the next video to do more. So I will see you there.